I'm going to be talking about some work we have been recently doing towards developing a high-level northbound interface for software-defined networks. So I'll start with some background information and lead up to the motivation of this work. So I'm going to first talk about network resource configuration. And the main objectives of resource configuration are first to meet the requirements of the offered services, such as bandwidth and delay guarantees. Secondly, to meet internal operator requirements, such as security and energy consumption, while at the same time achieve effective and efficient use of the infrastructure resources. I think everybody in the room will agree with me that it's resource configuration is a complex task. First, because we have a wide range of services which are offered over the internet. These have varying requirements. We also have a rich set of resources, both in numbers and in times, such as connectivity, storage, and processing. These have a large set of configuration parameters, and last but not least, we recently have the introduction of virtualized infrastructures, and their fluidity adds another degree of complexity. So network configuration is a result of business objectives, which are represented by high-level requirements. This process, of deriving network configurations is a manual process mostly. So we go from business objectives that come from the administration of a company. These are somehow represented with high-level requirements. They end up in two network administrators, which then have to come up with scripts that configure the network. And this process is cumbersome. So there are a few network management solutions for the configuration of resources. We have netconf, SNMP, a number of proprietary CLIs from vendors, and most recently we have had OpenFlow. But all these require low-level scripts that are not the easiest thing to write and then use that to configure so that the high-level requirements are met. So the current approaches have limitations. Those limitations are basically two. They're time-consuming. This is because there's no automation, right, to map the requirements, the high-level requirements to network configurations, and they're also error-prone. Because low-level scripts need to be written, it's quite likely that at some point in time the network administrators will introduce configuration inconsistencies. This will lead to services downtimes and so on. So it's a cost to the operator. And we come to intent-based networking. So this is a new sort of paradigm that aims to simplify the configuration process. And one of the most representative sort of descriptions I found in the literature is, don't tell me what to do, tell me what you want. So in other words, don't give me configuration commands, but give me your requirements, and I'll do it for you. So I'll be taking a simple connectivity service example throughout the slides, which is basically the intent, in this case, is just forward traffic from node A to node B with some delayed guarantees. So there needs to be the necessary translation sort of mapping mechanism in place such that those requirements can be translated to configuration commands. So this is the responsibility of the northbound interface in the software-defined network framework. So this is a simplified version of the SDN architecture here. We have some high-level requirements at the top. These go through a northbound interface. They end up in the management/control functionality, which computes the network configurations, and then the configurations are sent to the network elements through a southbound interface. So in the SDN world, there's a very well-defined southbound interface, which is OpenFlow, but there has been very little work on the northbound interface. So concerning the state of the art, both the ONF and some vendors have looked at the northbound interface, but they define basic properties and the structure of this interface, but nothing concrete is out yet. So northbound the intent sort of paradigm has its roots in policy-based management. This is something that we in the research community looked at between 2000 and 2010, and more specifically has to do with policy refinement. So the idea back then was that you have some high-level policies and you need to translate those to low-level policies that apply to network devices. However, at the time, the solutions that were developed were specific to some domains, like quality of service we looked at the time, and were not applicable directly in other domains. So the benefits, so if there's a process of automating the requirement decomposition through such an interface, it can result to a number of benefits, right? I mean, you can simplify the configuration process and at the same time avoid conflicting inconsistencies or configuration inconsistencies. And the fact that the whole process is automated can allow frequent changes to high-level requirements, which is not the case today, and also facilitate faster service deployment. So the main challenge to achieve that is to come up with the right abstractions, right? Just like OpenFlow, for example, deals with flows. I mean, the northbound interface has to deal with something else. So you need to come up with the right abstractions that will allow you to automatically map and essentially associate the high-level requirements to, first, management functions, the resources that you have in the network, as well as the commodities that you regulate. So taking the simple connectivity service example, we have a very simple network topology here. So the resources involved in the configuration of this topology here are the endpoints, right? It's the source and the destination. The commodity being regulated is traffic, right? And the management functions involved are two, the path computation and the path selection. So you first need to compute the paths from the source to the destination. In this case, there's 3 paths. And then you need to select the path that satisfies the high-level requirement, the delay constraint. So the delay constraint being 20 milliseconds, for example, then you need to take the middle path. Right, so I'm going to be giving some details of a solution we developed in the last few months. So let me first talk about the requirements of on a future network architecture. So we need to have the common abstractions that will allow us to expose the attributes or management functions and the services, right? We need abstractions to represent the resources and the commodities which are being regulated. And also, these will allow us to define or specify the high-level requirements and parse those requirements in the interface. So once those abstractions are in place, we need to have an implementation of a northbound interface that will allow us to automatically map the high-level requirements. So let me say that currently it's in an immature state, as I said before. So that led us to the work we have done in the recent past. So this is the system architecture we have. The upper block here is the northbound interface. It receives high-level requirements, and it's going through a 2-stage process. First, it maps to available services, then to management functions. The set of management functions selected are passed to a network management system, which computes resource configurations, and those configurations are enforced on the devices through a southbound interface. In the next slides, I'm going to focus on the northbound interface. So first, we need to define the high-level requirements. We use a general and simple format, which is inspired by sort of discussions within the ONF, but also based on a white paper from Huawei. So these 5 fields in expressing the intent or the high-level requirement. First is the predicate, which defines the actions to execute, like forward or store or process something. Then is the commodity, which is being regulated by the actions, like traffic or content. There's the target resources which are involved, like the switch, a switch and the server, some constraints on the actions, and also some conditions on the applicability of the action, like the value of a specific commodity. So in the connectivity service example, in that case, the intent can be represented like this. So you have the forward for the predicate, the commodity is traffic, you have two endpoints, you have the constraint of the delay, and then you have the condition being the traffic that comes only from a specific client. So as I said, the decomposition process or the mapping process goes through 2 stages. First, we map to available services, and the objective here is to somehow relate the high-level requirements, associate those with attributes of available services. Those attributes are captured in templates. We call those templates service descriptors, and they have 4 fields, right? Here is an example of a descriptor for the connectivity service. First, we have the operation, which is the basic functionality to provide the service. In this case, it's forwarding. Then we have the infrastructure requirements, which are decomposed into commodities and resources. And then we have technical specifications, which are the specifications on which a service must be operated. Again, they're broken down into commodities, resources, and constraints. And last, we have the performance affecting factors, which are the factors dominating, the dominating factors which affect the performance of this service. So all these fields, like the operation, infrastructure requirements, and the performance affecting factors are static. They are defined when this template is formed, but this here, the technical specifications in italics, they are quantified when there is a matching service. So the service mapper has 2 components. First, the resolver, which it determines the descriptor matching the requirement. So it reads the various service descriptors. It has, okay, for simplicity, I'm just going to say that this is a matching operation between the predicate of the high-level requirement and the operation of the service descriptor. And once such a matching is found, we can say that we have found a service that basically relates to the requirement. Once this is done, the instantiator, the bottom component here, updates technical specification fields, the commodity, the resource, and the constraint. So as an output, the selected service descriptor is sent to the management function mapper. So the management function mapper has 2 components. Again, I'll show those in the next slide. But in the same way that we have descriptors for services, we have descriptors for management functions. So there's four fields. The example here is for a path selection function. So we have the commodities, which define the type of commodities regulated by the function. We have the resources, which are configured by the function. We have the function. We have the operations, which are performed by the function on the resources and the commodities, and we also have some performance factors affected by the decisions of a specific function. So in this, the path selection case, we have the commodity regulated being traffic, the resources is the switch and the link in the network, and connectivity delays is the performance factor which is affected by this function. So again, in the function field, we have some parameters that once a function is matched, those are instantiated. For example, here we populate the endpoints that we select as a path, and we also include the delay constraint. So the resolver in this case determines the function descriptor which matches the selected service, and to do the matching, we use this rule here. So the commodity part of the function needs to match the commodity part of the service. The same applies to the resource. And last but not least is the OP and the path fields need to match. So once it's a match, the function or the set of functions are sent to a selector here that basically can filter them out based on prior knowledge, on a knowledge base here that is populated by the operator. Based on past experience, for example, the operator may know that a specific function may not affect, may not have a big effect on a specific requirement, so it can be dropped, or in other cases, if there's a set of functions that satisfy the requirements, the prior knowledge will say how those functions should be executed in a specific order. So the output of this block is a set of selected management functions, and this is sent to a management system. The management system is responsible then to find the right configuration. Some algorithms are in place in most cases, and later on the configuration is enforced on the system. Right. So I'm just going to go through some couple of use cases for demonstration purposes and some evaluation results. Let me say that we have experimented on a very simple topology, a toy topology of a few nodes. Implementation-wise, we have used Mininet for the topology, the host, and the switches. We have a RESTful API to interface the network management system with Mininet. So that we can send the commands we need. For the southbound interface, we've used a small set of POX controller APIs. Both the high-level requirements and the descriptors are specified in JSON, and we used iPerf to emulate fixed-rate UDP client traffic. Right, so the first use case is the connectivity service with some delay constraints. So simple topology here. Initially, we have two clients sending traffic from node 1 to node 6. There's no delay requirements to start with, so all traffic is sent over this path. So there's 3 paths in here that have already been established. The path on the top, the red one, has a delay of 60. Path 2 has a delay of 40, and the last one of 50. So at some point in time, client 2 may decide to switch to another service, right, to a more advanced service. So what happens is that, so this advanced service requires a delay of 40 milliseconds, let's say, right? So what happens is that all client traffic must be shifted to another path. So in this case, a path selection function is triggered, which basically shifts traffic from the upper path to the middle path. And this is demonstrated on the plot on the right. So you see initially we have 1.5 megabps of traffic on the red path. At time T20, the new requirement is inserted in the system. And at this point, there's a small gap here. Then the new traffic from client 2, which is half a megabit, is sent over the green path. The second use case has to do with traffic redirection through a security virtual function. So we have the same topology. Now, in addition, we have 2 servers, S1 and S2. S1 is running an augmented reality application, which is accessed by client 3, and client 3 is basically served locally. It doesn't generate any traffic in the network, but we have client 1 and 2, which send traffic over the upper path. So at some point in time, the operator may decide that additional security needs to be in place, so all traffic in the network should pass through a DPI point. So it first needs to install the VNF somewhere, right? So it chooses to go for a least utilization server policy. So because this is already running something, the function is instantiated here. And then all traffic needs to be redirected through this function. So in this case, there's a few management functions which are invoked. So it's the placement of the function is the server selection. It's path instantiation, because this path, the blue path, did not exist previously. And then path selection, so that traffic from these 2 clients is forwarded over this path. And as you can see on the plot here, we have initially all traffic going on the red path. At time t equals 25, the new requirement is inserted, and there's a small gap here until traffic from the clients, all the traffic from this path is redirected to the bottom path. Right, so some conclusions. Northbound interface for SDN is of paramount importance. Currently, things are not concrete. There's, of course, a number of benefits which are associated with that. It simplifies hugely the configuration process. Things can happen more frequently. But to do that, we need to have the right abstraction level, and we have to have an implementation of the interface. The solution we have is lightweight. It's currently like, okay, it's simple, but it's like less than 1,000 lines of code, and it's fast. So when I was pointing to this gap here, right, this is the amount of time that is needed for the new configuration to be enforced. And this takes 2 or 3 seconds. But the majority of that time is used by the management system to determine the configuration and the southbound interface to install it, right? So the whole translation process is really, really fast. The time complexity is constant with the number of services and functions, so this is not an issue. And let me just finish with some future work. Of course, we plan to experiment with more realistic topologies instead of these toy topologies we have used until now. We plan to deal with competing requirements because these can arise, right? You can have requirements inserted by the administrators that are conflicting or contradicting. And we also need to implement some feedback mechanism from the management system. Basically, if an intent at some point in time it stops being served in the network, right? You need to have some feedback to say that things are not working and a new configuration is needed. So that's my presentation. Thanks a lot. If you have any questions, I'll be glad to answer.
Questions, anyone?
Yeah, thank you, Marinos. Very interesting piece of work. Okay, I just want to get clarified. Okay, so whether you are doing path selection or path computation, so does it mean whether you upon a change of requirement, you need to carry out some computation to engineer out new path, or you simply just look up the existing solutions to which are pre-installed?
Yep.
And just activate that new configuration.
Yeah, it depends if the path is installed already. Right? If there's a path established, you just need to select.
Yes.
Right?
Okay.
So, but as in the second use case, right? Let's say that the path did not exist through a specific point you want to go through in the network, then you need to compute a new one, right? So you need to trigger more than one functions.
Okay, yeah, so I think for the second scenario, probably, I'm very interested in the capability of, let's say, dealing with more complicated requirements. Just for instance, in, let's say, this kind of, let's say, constraint-based routing, for instance, if you have even 2 additive coarse metrics, basically it's an NP-hard problem. Okay, right. So basically, I'm very interested in what would be how promising the system.
This is not down to the northbound interface, right? The actual configuration is in the Netman system, right?
Yes, that's right.
So they are, okay, fine. It is there might be complexity in that, but that's down to the Netman system.
Right.
And I guess currently, I mean, there are some solutions in place, right?
Okay, so probably the management system will have some sort of, let's say, top level of judgment on what sort of requirements that could be potentially handled by such a system.
Yes.
Okay, yeah. Thank you.
Thank you. Thank you for explaining a bit more about the intent-based networking concept, because I've heard a lot about it, and that's the clearest explanation I've heard so far.
That's my take.
But you did also mention some work that Huawei had done. Perhaps it was the NEMO project you were referring to. And you also mentioned ONF. And neither of those movements are currently active. the ONF transferred the people who were involved in intent-based networking, who had been working under the auspices of the ONF, are now doing that activity under the MEF. And the NEMO project, as I understand it, failed to get any other industry participants involved outside of Huawei, and so you really need to get a number of different organizations in order to create a new standard. So with that, do you think that there is scope under ETSI or some other body to create a standard to support these abstractions, or is it still a science project?
Well, currently there's some movement in the ITF, right? So people are still working on these issues, right? And there was a meeting during the summer as well. I think it was where was the meeting? The previous one, Canada or the US? So things are happening, right? Things are moving, let's say. I'm not so sure about the right motivation for the companies to get involved, but definitely there is plenty of scope to do work in this area because it can bring quite a lot of benefits for operators. It will make their life much easier. So maybe in that respect, the operators need to push a bit more, right? They need to push a bit harder so that a solution for this can be found.
Okay, we can chat later. Thank you.
All right.
Thanks, Marinos.
Thank you.
So this is the end of pre-lunch session, and we'll reconvene at 1:30 after lunch. Thank you.